Welcome to the complete lecture for Chapter 1 of Chemistry 150, and I'm really glad to have you here. This is going to be a fun course, and I want to remind you that if you have questions on anything, please let me know. I'm happy to help. The website for this class is mhchem.org/150. There's a lot more materials on there and more information on the class, and I do encourage you to purchase the Chemistry 150 companion as soon as you can. We'll talk about all of this more in lecture, but for right now, let's get on to the Chapter 1 complete lecture. So chemistry is the study of both matter and energy, and people usually will see the matter part. They think of atoms and the periodic table, but it's also about energy as well, and that's something we'll talk about as we go through the course. The earliest designation of chemistry is, I'm going to probably mispronounce it, I think it's chemia. It's an ancient Egyptian process, how they used to take care of dead bodies, embalm them. And later on, the processes that were developed there were applied to metallurgy. So as they made spears or swords or whatever, that kind of stuff. So chemistry's always been involved with chemicals, big surprise. And chemistry, and then chemia, of course, was often seen as kind of an occult thing because, dead bodies and taking these raw minerals and putting them into cool things and stuff, that was seen as kind of superstitious even. Here's some different names that have popped up and how chemistry, I think the name is done, and I'm not like a linguistic master, so bear with me, but you can see here that chem, I guess it is an early way of saying earth, and then chemia is the transmutation of like bodies and stuff like that. Alchemia was actually an Arabic term, apparently, that was used for the chemistry process. And then alchemy, which we'll talk about more on the Chem 200 level, alchemy was kind of like an early form of chemistry. They were more interested in like turning everything into gold, but that's another whole story. Boyle was an early chemist, and in 1661 he created the Chemistry publication. He used a Y, but we're not going to hold it against him because everybody didn't have running toilets at that time, let's be honest. And then finally, chemistry came out and stuff in the way that we're used to now. Chemistry is seen as the central science because it's really involved in many other fields. Some fields are kind of isolated from others, but man, chemistry is everywhere. Chemistry is definitely a big part about biology. So biology uses chemistry to explain how the cells move around and how we breathe and stuff like that, which of course is biochemistry as well. And medicine, oh my gosh, yeah, you couldn't do hardly anything with medicine without the understanding of chemistry, and we'll see that in future courses. Now, nuclear chemistry is a very special form of chemistry that's involved in the nucleus. Chemistry of the nucleus is a very high energy form, so there's some scary and some cool things that come out of it. So of course, nuclear bombs, that's bad, but there's also a lot of imaging of the body that comes out of nuclear chemistry, so there's some good and some bad things, like with everything. Physics is huge when it comes to chemistry. Chemistry and physics are both what they call physical sciences, and so we're really involved with measurement and details and stuff like that. So physics and chemistry definitely overlap, and we'll see examples of that. Astronomy, which is one of my personal favorites. Astronomy uses chemistry as we begin to explore the stellar mediums and other planets and stuff. We use the chemistry to understand the things that we see, which is really cool. Geology, of course, definitely big time in chemistry. You can't understand the flows of lava and why some lava is slow moving and some lava is fast without understanding chemistry, which is cool. Environmental science, which is big time important. All the pollution, you have to know about chemistry. And of course, the plant sciences, which is also part of the environment, need chemistry too. You have to know the right kind of nutrients getting into the plants and why some live and some die, etc., etc. And these are just a sampling. There's other ones too, but chemistry is big time important for many things, not only in science, but all around you as well. In chemistry, we split all the different types of chemistry into more or less 5 types, all right? And we'll talk about some of these even in Chem 151 and a lot more in the 200. There's organic chemistry, which is basically the chemistry of carbon, nitrogen, and oxygen. There's inorganic chemistry, which is metals. And I'll be honest, I'm very biased. I consider myself to be an inorganic chemist. So I studied metals a lot. I have nothing wrong with carbon, but carbon gets a lot of attention attention, as we're going to see. So metals are really cool and the colors are beautiful. But anyway, you're seeing my bias, so I'm just going to shut up. Inorganic chemistry is the study of metals. Organic is mostly carbon and some of the non-metals, and we'll talk about what this means later. Now, analytical chemistry is a really cool field, and this involves things like spectroscopy. And in analytical chemistry, it's nice to know like how much and what kind of something. And without analytical chemistry techniques, you wouldn't be very useful in figuring these out. It's a very cool field. If you like shows like CSI and the different forensic kind of shows, they're always using analytical techniques to determine blood and stuff like that. It's really cool. Now, physical chemistry is important. Physical chemistry is where essentially physics, chemistry, and calculus come together. And it's a real important field because a lot of the things that are modeled in chemistry come from studies in physical chemistry. It's generally seen as a tougher one because those are pretty intense fields, and all three of them coming together, goodness, it's crazy, but it is a powerful field, and it is a distinct part of chemistry. Now, biochemistry, or biochemical chemistry, if you will, is the chemistry of life, and I think this is the most up and coming of the fields right now, and this is obviously important. It's where biology and chemistry come together, and there's so many cool things, protein folding and DNAs and all kinds of stuff, so that's a neat field. And there's other ones too, like geochemistry, astrochemistry, so geology and chemistry, or astronomy and chemistry. Radiochemistry is not tuning in your radio, darn it, but it's radioactive chemistry, the chemistry of the nucleus we talked about earlier, and also medicinal chemistry. Medicine chemistry is huge, lots of names like that. If you're going to do anything in chemistry or physics or basically any of the sciences, you've got to know how to make measurements. And to make measurements, you have to have some way to quantify them. And so the metric system is by far the preferred system for measuring things in science. And some of you, I'm sure, grew up with the metric system, and this is like a no big deal kind of thing. But if you were like me, who grew up in Gresham, Oregon, I didn't do that much with the metric system. And it took me a little bit longer to kind of figure things out. So the metric system is a super easy thing to use once you get used to it. And I'm a convert to this. I wasn't born this way or anything, but it really is pretty cool. And to understand the metric system, you have to understand the metric prefixes. Now there's a whole bunch of them, and I put several of them right there. Notice, for example, here's kilo. All right, kilo is one you might be familiar if you've heard about a kilometer. So if you're in Canada, distances aren't usually measured in miles, they're measured in kilometers. And you can see if you go over on the right that there are 1,000 kilos. 1,000 and kilo go together. Or if you want to be cool scientific notation, that's 10 to the third. So because a kilometer is based on the meter, the base unit, a kilometer would be 1,000 meters. All right, and that's literally all there is to it. So a kilometer, 1,000 meters. A centimeter is probably one you've heard of before. A centimeter is 0.01 meters. So a centimeter, of course, is much smaller. A kilometer is much bigger. And there's other ones. Here's nanometer, which you may or may not have heard of before. In biology, they use micro a lot. That's important. Milli, like a millimeter, is important. So there's all kinds of these metric prefixes. Now you can see that I highlighted 5 of them there. Kilo, centa, milli, micro, and nano, because we're going to use those 5 a lot in chemistry. And they all have a metric prefix over there. And we'll talk about how these work here in a little bit. But just realize that if you see a nanosecond, all right, now it's nanosecond, as a second is a base unit. A nanosecond means you'd have 10 to the minus 9 seconds. So it's a very, very, very small amount of time. And we'll talk more about what this means later. Most of these metric prefixes are pretty chill. So like kilo is K and centa is C, et cetera, et cetera. Micro gets a Greek symbol. It's usually pronounced mu. It's like a U with a long line to the left of it. So micro has mu. So sometimes you see other things, but that's what it's supposed to be anyway. We'll talk more about these later too. So again, here's examples of how you can change the base unit and have these relative kind of things figured out. So earlier I talked about a kilometer, all right? So a kilometer would be a length of mass, and the kilometer in a centimeter, all right? A centimeter would be a small amount of mass, or length, I'm sorry, not mass. Mass is right next to it. Duh. Mass, the base unit, is called a gram, which I'm sure you've heard of. And a kilogram is related to the gram in the same way that a kilometer is related to a meter. So if there are 1,000 meters in a kilometer, there are 1,000 grams in a kilogram, which is really cool. And you can do the same thing for the centigram. There were 10 to the minus 2, or 0.01 meters in a centimeter. So there would be 0.01 or 10 to the minus 2 centigrams in a grams. But we're not done yet. You can also do it for volume, which is how much space something takes up. You can do it for time, which I did kind of babble about a little bit. Here's that nanosecond down there. And there's all kinds of other base units you can use. But the important thing here is that those relationships are all the same. Kilo is always 1,000. So if it was kilo zap, and who knows what a zap is, that would be 1,000 zaps. And a centazap, and who knows again what a zap is, but a centazap would be 10 to the minus 2 zaps. So those relationships work all different ways with all kinds of base units, which is really cool in science, where we have lots of different things that we measure. These up here are going to be the most common, especially length for meter, mass, which is grams, and volume in liters. But there's other ones too. This just highlights some of those relationships. So again, you can see here how a kilometer is 1,000 meters. And again, we'll talk about scientific notation, but 10 to the third is the short way to do 1,000. And we talked also about centa. Here, centimeter is 0.01 meters, all right, which is the same as 10 to the minus 2. Now, for centa, what happens a lot is a lot of people will say 100 centimeters equals 1 meter. And believe it or not, that is the same as 1 centimeter equals 0.01 meters. Notice that 0.01 meters, if you would divide that by 0.01, 0.01 divided by 0.01 is 1. That's that. And 1 divided by 0.01 is 100. You can do that in your calculator if you're not sure. So it's very common to see 100 centimeters equals 1 meter. It's the same exact thing. And again, this would work for centigrams and grams as well, or kilograms to grams, or anything like that. Again, notice here's the ones we're dealing a lot with. Here's a millimeter, all right? And a milli is this 10 to the minus 3, or 0.001. Now, if you do the same kind of trick you did with centa, 10 to the minus 2 divided by 10 to the minus 2 is 100. If you go 10 to the minus 3 divided by 10 to the minus 3, you'll just have 1 meter on the right. And 1 divided by 10 to the minus 3 is 1,000. So a lot of times you'll see like 1,000 millimeters equals 1 meter, or 1,000 milligrams is 1 gram, etc., etc. And there's milliliters, which is what you probably see on soft drinks and stuff like that sometimes. A milliliter is just 1/1000th of a liter, or there are 1,000 milliliters in a liter. Micrograms and nanograms, or the micro and nano prefixes, will come in kind of handy once in a while. The micro is 10 to the minus 6, and the nano is 10 to the minus 9. And so 10 to the minus 6, if you put that on the other side like we have before, that's a million. So there's a million micrograms in a gram, and a nanogram, 10 to the minus 9, if you do 1 over that number, you're going to get this number, which is a billion. So there's a billion nanograms in 1 gram. And all of these ways are sometimes methods you'll use in these kind of courses. If everyone used the metric system, it would be totally cool, but there's a lot of people that don't. Big surprise. And America, of course, is one of them. And again, I grew up kind of not knowing any of them. So sometimes we will have to deal with things like inches and miles and pounds and quarts. And there's commonly bridges that go between them. And if you have to convert, say, inches into centimeters, it's 2.54 centimeters equals 1 inch. If you're a runner, you may have done like a 5K or a 10K, and you're like, how many miles is that? No problem. 1.61 kilometers equals 1 mile. So you can go back and forth. There's 454 grams in a pound, and a liter, if you have to convert to quarts, 1.06 quarts. So roughly a quart and a liter are the same. Now, in this class and in all chemistry classes, you really should try to use the metric system at all time. And I'm going to push you that way in this class a lot because it's so easy to use. I promise I hope you're going to love it anyway after I'm done with it. So I wanted to show you it's really cool. Best thing since sliced bread. But anyway, try to use the metric system if you can at all times. But there are ways to go back and forth if you need to, especially in the United States. So a physical quantity is, and again, a lot of this stuff is probably pretty simple to you, but I want to make sure everybody's starting off on the same page. So a physical quantity is just something that you can measure about some kind of system. It's a measurable physical property. And some of these you do yourself all the time. So if you want to know how tall you are, that would be height. Or maybe you want to know the volume of a rock you picked up in the desert. Or if you're just curious what the temperature is outside, all of those are physical quantities. All right, they represent some kind of system, and you can use, for example, a thermometer for knowing the temperature, or you can use a ruler stick for finding your height, etc., etc. All these things have different ways you can do them. So here's an example of 61.2, and that number by itself wouldn't be very helpful without the unit that goes with it. A kilogram, as we saw, is 1,000 grams. So you need both the unit and the number at the same time if you're going to be a good scientist. So when you're doing physical quantities, you should have the number and the unit at the same time. If you had just a weight of 1, all right, like if you had that number, whoopee, what does that mean? Is it 1 year? Is it 1 atomic bomb? Is it 1 shot of espresso? I mean, what the heck is it, right? You have to know what it is. And that's where, of course, the unit comes in. And you have to also know, like, is it mass or is it volume? Is it a kilogram or is it a pound? So when you're having a physical quantity, you've got to have both. Know both the number and the units. And try really hard in chemistry to always put the units with the number, because without that, that might be super confusing. And again, it's confusing because there's so many types of units. All right. So for example, for mass, you could have masses in pounds, kilograms, ounces, grams. Of course, you could measure yourself in nanograms if you wanted, but it would be a crazy type of unit. Anyway, so scientists were at first really confused by all this too. So this group got together, the International System of Units, or as it's abbreviated usually, because it's French as I understand, SI units. And SI units is just a way that all these units, if you have to pick one as a scientist, you try and pick an SI unit. And those will help scientists to understand you easier than if you don't use an SI unit. So an SI unit is just like the best kind of unit to use. And I'll be honest, chemistry sometimes doesn't always use the SI units, but overall we try, like all the sciences, to use SI units whenever possible. I think physics does the best job of following all SI units. Chemistry does a pretty good job, but we'll talk about why there's some exceptions later. So in SI units, if you're going to measure a mass, like how much mass is in a system, you want to use the kilogram. And this is the one where chemistry doesn't do as well. We use a lot of grams. So kilogram is the SI unit. It's the best one to use, but sometimes grams is used too in chemistry. If you're going to do length, you should measure it in meters. So So don't use feet or yards or even kilometers for that matter. You want to try and use meters. Volume should best be expressed in what's called a cubic meter. This is another one where chemistry doesn't do as well. We do a lot of things in liters and milliliters, and a meter cubed is not either of those, but you can convert one to the other if you need to. It's not too bad. And time should be measured in seconds. Now, if you see other types of units and stuff, a lot of times they are derived from SI units. So as an example, if you're measuring the speed of something, your car, how fast you run, how fast the atom goes to the molecule, whatever, the best one to use is meters per second. Density, which is how much mass an object takes up per unit volume, we'll talk about that more later, is grams per centimeter cubed. And notice here how centimeter cubed looks kind of like a meter cubed. A centimeter is smaller than the meter, so a centimeter cubed is smaller than a meter cubed. In chemistry, grams per centimeter cubed is really handy. But anyway, we'll see that. But the punchline here is that if you can use SI units, there are some advantages, and we'll see this, especially in Chem 221, but a little bit in Chem 151 as well. If you're going to measure mass, all right, you need some way to measure it, and it's usually done on some kind of a balance. And mass and weight, and this is kind of somewhat nerdy science, I apologize. It's technically mass and weight are different, all right? Mass is how much matter an object has, and weight is actually a measure as to how gravity affects an object. Now, sometimes at OMSI and places like that, if you've been to there, they'll have like, what do you weigh on the moon? And your weight is different on the moon than it is on the Earth, and it's different on Saturn, and it's different in space, and et cetera, because really weight has a gravity component to it. Mass is mass regardless of where you are. So if you have 30 grams of mass, it will be 30 grams of mass on the moon and 30 grams of mass on Saturn. If you have an object, which is, we'll say 100 pounds, that's a weight, all right? And technically, 100 pounds on the Earth is different than 100 pounds on the moon, which is different than 100 pounds on Saturn, et cetera. So if you have two objects with identical masses, all right, and you're at the same location, they're going to have identical weights. So what this means is that if you're on the Earth and you're about the same elevation, the weight and the mass will be the same if you have them. They're the same thing. However, if you went to the top of Everest, you'd probably have enough of an elevation difference that your weight would change, but your mass will be the same, all right? So what that means, again, 30 grams here in Gresham, Oregon would be 30 grams up on Everest. However, 100 pounds in Gresham, Oregon may not be 100 pounds up on Everest because actually the gravity is a little bit different. So the punchline of this slide, chemists try to use mass whenever possible. We're going to use grams and kilograms and stuff like that because that's a great way to measure it. It works great on top of Mount Everest or down, and if we're ever on the moon or Mars or something like that. And I think these kind of ways, this is your instructor's way of thinking. So these are all possibilities and the masses would be the same, but technically weight is different. So usually we try and talk about things in mass. Now, length is another one. And again, the SI unit for length is the meter, all right? And they've got really cool ways to calculate what a meter is and stuff like that. You can convert meters into other systems. So a meter is 39.37 inches, and you can convert meters into anything, miles or distance between two atoms. I mean, whatever you want to do is totally fine. The centimeter and the millimeter are used a lot. These are ones we use kind of in our day-to-day lives as well. A centimeter is 1/100th of a meter, like we talked about earlier, and a millimeter is 1/1000th of a meter. So there's 1,000 millimeters in a meter, and there's 100 centimeters in a meter. And these are the ones we'll use most of the time. But sometimes, again, we will see some other ones, especially the kilometer, the micrometer, and the nanometer, but we'll deal with those when we get to them. If you're going to measure volume, this is another one. All right, and volume is used for liquids, which is really cool. All right, they fill up so much space, but it can be used for solids and gases as well. We'll talk about all of this later. Now, the SI unit for volume is the meter cubed. All right, and I'm going to be totally honest, we don't use the meter cubed that much in chemistry. What we use most of the time is the liter and the milliliter. All right, there are 1,000 milliliters in a liter. So that's a real common kind of conversion. If you have to convert it over, 0.001 meters cubed is the same thing. And also, another type of unit we'll use a lot is called a centimeter cube. And a centimeter cubed and a milliliter are the same. So if you had 30 milliliters of coffee, that would be 30 centimeters cubed of coffee. You can interchange the units with no problem. You wouldn't want to do that with meters cubed or liters without converting it, all right? But with milliliters and centimeters cubed, you can. We will use the liter, the milliliter, and the centimeter cubed a lot in chemistry, and it's all about how much space an object takes up. Here's a little picture. The left-hand side is a meter cubed, and a cubed is the same as a meter times a meter times a meter. That's the same kind of thing. And notice here how the height, the depth, and the width of this kind of orangish cube, they're all supposed to be 1 meter. So if you have 1 times 1 times 1, that's 1, and meter times meter times meter is meters cubed. That's really what a meter cubed is, all right? So that's a representation of what a meter cubed is. Now, what scientists use a lot, like I said though, is we mostly use liters, and we mostly use milliliters, which as I said was the same as a centimeter cube. So notice if you take just one of these blocks, all right, from the meters cube, that gives you what's technically a decimeter, but even chemists don't usually use this. Anyway, a decimeter cubed is the same as a liter. So it's like roughly 1,000th of a meter cube. And then if you take just one small little square from that one, that's what a centimeter cubed is. And a centimeter cubed is a milliliter. So if you're curious and stuff, that's what all of them represent. We've used some of this already, and you've heard of these before, but in chemistry, we're kind of in a unique place because we use some numbers which are just massively big, and we also use some numbers which are massively small. And to designate all these different things and to avoid getting trapped in counting zeros, which I hate, and all scientists should hate, by the way, too, in my opinion. But anyway, you should start using what's called scientific notation. And scientific notation is just a great way to express very large and very small numbers without getting lost in the zeros. And I'll try and show you examples of this. Now, if you want to write a number in scientific notation, it's pretty easy. First of all, in scientific notation, you have a decimal point. And to the left of the decimal point, you have a number between 1 and I would say 9, although this says 10 right here, that's okay. And then to the right of it, you can have a decimal something else. And that's multiplied by 10 raised to a power. And the power, the little number that's the superscript, it's called an exponent. And the value of the exponent will tell you if you have a number that's larger than 1 or if it's a number that's less than 1. So remember that from math, 10 to the 0 is the same as 1. And again, if you don't trust me on this, it's totally fine, by the way. Enter in your calculator 10 to the 0, and you'll see it comes out as 1. So if you have a number, you start off by just multiplying it by 10 to the 0. So you could have like 35 times 10 to the 0. And then what you want to do, you want to move your decimal point so you have just a number between 1 and 10. So for 35, that would be 3.5, all right? And notice as you go from 35 to 3.5, you move it to the left one spot. If you move things to the left, you're going to make that exponent, that little tiny superscript thing we saw earlier, you're going to raise it by the number of places you move it to the left. So in this case, it would be 3.5 times 10 to the first. And then if you do it more than once, you just change it. So down here is an example of 215, and we want to turn that into a scientific notation. So we'd start off by writing 215 times 10 to the 0. And you can see at the bottom here, we're moving a decimal over to the left 2 spots. So it becomes 2.15. And because we moved it 2 spots, you'd have a 10 to the second right there. All right. So moving the decimal to the left means you're going to have a positive number for that little exponent, which is really cool. This also means that if you see a number in scientific notation with a positive number, so 2.998 times 10 to the 8th is a positive number, that means it's a big number. It's bigger than 1. But in chemistry, we do deal with numbers that are a lot smaller too, and we'll talk about that in a little bit. So let's practice here for a second. And if you want, you can pause this video and practice along with me. Let's write 120,000 in scientific notation. Okay, no problem. So what you would do is you'd start off by writing it 120,000 times 10 to the 0, okay? Now, it doesn't show the decimal explicitly in this number, but it would be right there. That's why you know it's 120,000. And what you would do is you want to write this number as a number between 1 and 10. So we're going to move it 1, 2, 3, 4, 5 spots. We're going to write it as 1.2 times 10 to the 5th. And that 5 means that we moved it to the left 5 spots. And that's literally all you do. It's pretty chill. For this number, we want to write a number which is much less than 1 in scientific notation. So for this number, you'd start off by writing it as 0.000012 times 10 to the 0, just like we did before. But this time, as you can probably see, we're going to move it to the right, not the left. We're going to move it 1, 2, 3, 4, 5, 6 to the right. Now, if you move to the right instead of the left, that means you're going to have a negative exponent. So notice down here, 10 to the minus 6 is what you want to see for the answer. All right. You don't want to see the 10 to the positive 6. That would be a big number. So small numbers, same kind of thing as the big numbers. You're just going to have a negative exponent instead of a positive exponent. And this is really handy. Sometimes you want to turn non-exponential numbers, start again. Here's an example of how we can turn a scientific notation number into a regular number, or a number without an exponent. And again, it's pretty easy. You just want to move the decimal point the same number of places as the value of the exponent, and then get rid of the exponential part of the number. So that's probably about as clear as watching paint dry. Let's do an example. All right. Oh, if the number is positive, we move the decimal to the right, same numbers as it would be. So instead of going left for the bigger numbers, we're going to go right. And then if the number, of course, is negative, we'll move the value to the left, kind of like in the example we just did. And you should have a number which is pretty small, much less than 1. All right, now here's an example of turning a small number into a regular number. So 1.56 times 10 to the minus 8th. So what you want to do is just start off with 156, and to move that decimal, the 8, the 10 to the minus 8, means move to the left. So we're moving 1, 2, 3, 4, 5, 6, 7, 8 spots. You're going to have 7 zeros. The 1 was initially to the right of the decimal, or to the left of the decimal, excuse me, but we're moving it to the left. So you're going to have a really, really small number. And this is why, of course, scientists love using scientific notation, because man, oh man, you can turn lots of zero numbers into something that's manageable. Scientists are not going to sit around and and count all the zeros. This example was actually broken down into groups of 3. So like here's 3 zeros, etc. Most of the time numbers are not that way, and it's very confusing to check out. So scientific notation can be pretty helpful. Now, before we go any further, I just want to advertise something. All modern calculators have a function that allows you to go from a regular number to a scientific notation number, and also from a scientific notation number back to the regular number. And I've had a lot of TI, Texas Instrument Calculator experience, and it's usually something about the form, and it's like there's the regular form and the scientific form, and there's a little button that allows you to go back and forth, and every calculator is different, so I can't really tell you what it is, but I highly encourage you to find out how this works, because if you get a number with tons of zeros, you might copy it down wrong, but if you can convert it into scientific notation, it's really easy to write down the answer there. So figure out on your calculator, whichever kind you have, how to go from a regular number to scientific notation and vice versa, and it will save you a lot, not only in Chem 151, mind you, but all of the Chem 200 series. So let's write 1.23 times 10 to the 6 in a non-exponential form. Okay, no problem. So we know that 10 to the 6 is going to be a big number. So we're going to have a lot of zeros to the right of the 2, 3, and we're going to move those decimals over. And that 6 means we're going to move the decimal 6 places to the right. So we'll start off by moving it 1, 2, so we get 123. That's 2 of the 6, but we're going to go 4 more spaces, and you can see how this number is 1,230,000 if you write it out in non-exponential form. And again, once in a while it's cool to go back and forth. Normally we love scientific notation, but it is nice to go back and forth. Here's another example, 1.11 times 10 to the minus 5. Now we know that this is a number much less than 1, so we're going to have lots of zeros to the left of the 1.11, and one of them is going to come from moving the decimal to the left 1, and you've got 4 more zeros after that. So this one, 0.0000111. My little hint down here is the bottom and stuff. Remember that if the exponent is basically a positive number, it's going to be a number larger than 1, and you're going to have a lot of zeros to the right. On the other hand, if that's a small number, you're going to have a negative exponential number. You're going to have a lot of zeros to the left. So it kind of helps you to figure out which direction you want to go. Calculators are really cool and stuff like that. They can be your friend. And again, I really highly recommend that you figure out how to go from scientific notation back to regular, and from regular back to scientific notation. If you can do that, I will consider your experience in Chem 151 to be a success, because that's a really important thing. Now, sometimes you get a number which has lots and lots of numbers associated with it, and sometimes we have to round up or round down the number, and we'll talk about this more here in a little bit. But for right now, if you do have to round a number, if the first number you're going to drop is between 5 and 9, then you want to round up, go up 1 unit. But if it's between 0 and 4 that you're going to drop, you don't do anything. And we'll show this here in a little bit. So in your calculator, all right, what I would do is try going 1.5 times 10 to the 5th times, which is what the parentheses mean, 1.2 times 10 to the minus 2. And when you put this in your calculator, you almost undoubtedly have something that looks like EE. It might say EXP. It might be 10 to the X. But I want you to practice this in your calculator. Get your calculator out. Pause my video. All right, get it out and try this problem. If you enter 1.5 times 10 to the 5th and you multiply it by 1.2 2 times 10 to the minus 2, you should end up with a number which looks something like this, all right? We're going to round here to just 2 digits. It should be 1800, or if you prefer, 1.8 times 10 to the third. And those will be inches cubed because you have inches squared times the inch. But all I really want you to do is I want you to have practice with your calculator. If you can get this answer, 1800 or 1.8 times 10 to the third, you're good to go. And again, you might have to round something, and that's quite all right. If you can't do this, contact me. I might have some ways to help. It should be no problem. Sometimes it's a second function, EE. There's lots of different ways to do this, but man, is this important in chemistry. You've got to be able to do this. So if you can't do this problem, don't despair. Reach out to me or talk to the tutors and stuff like that. We've got to make sure we can make you do this. Here's another one just to practice. 4.3 times 10 to the fifth divided by 5.1 times 10 to the minus 6. Now, this problem is a little bit different because, well, first of all, you're dividing, of course. However, what I want to focus on is you're dividing by a scientific notation problem. If you've done the EE or the EXP button correctly, all right, you're going to get a number which is 8.4 times 10 to the 10th, and that's what I want you to get. However, if you actually enter in 4.3 times 10 to the fifth, divide 5.1, and then you push multiply 10 caret negative 6, you're going to get a much different number. You're going to have 10 to the fifth times 10 to the minus 6. It's going to be a number roughly about 1, a much smaller number. And that's not the right answer. The 10 to the negative 6 goes with the 5.1, all right? And the way you were doing it before is you're trying to multiply by 10 to the negative 6, which is wrong. So if you don't get this number, I want you to email me, all right, and just say, hey, I'm having problems getting this number. One thing that you can try is you can try putting parentheses around that whole part. If you go 4.3 times 10 to the fifth, divide, parentheses, 5.1 times 10 to the minus 6, parentheses, that's another way of doing it. I would prefer that you use the EXP or EE button, but if you don't, let me know and Stefan will figure it out. Now, in chemistry, there's always a little bit of uncertainty when it comes to measurements, and this is where the rounding part is going to pop in, by the way. So this is a graduated cylinder, and let's say I asked you, how many milliliters of water are in the graduated cylinder? And you can see on the side of the graduated cylinder that there's these little graduations, and right now this is a milliliter graduation on the graduated cylinder. So it would be like 15 milliliters, 20 milliliters, etc., etc. So you can see here that if 15 is there and 20 is there, 15, 16, 17 would be right there, and that right there would be 18. So we would all say it's somewhere between 17 and 18. I don't think that's a problem. But what is, if we wanted to go further, like is it 17.5? Is it 17.4? Is it 17.6? And this is where a little uncertainty pops in. And this is not a function of you like learning chemistry for the first time or something like this. This isn't a deficit in like your science ability. This is a normal thing that all people go through when they make measurements. So what I'm introducing here is that making a measurement may not be as simple as you thought. We can all agree that that is between 17 and 18 milliliters, but is it 17.5? Is it 17.4? Is it 17.55? You know, what level of control do we have over the measurement? And again, all measurements are this way. It's not just volume, it's length and everything else. So scientists and chemists especially have to take this into account because our field is so measurement based. So this introduces probably the most important topic of all Chem 151, and it's called significant figures. And sig figs, which is the abbreviated name, is really, really important. It's not super exciting, all right, but it's a really important part of chemistry because almost all of our measurements are really important based on things. So in a measurement that's made to indicate the precision, which is how close of a value we have, all right, we're going to use all the digits we can. And really, it's all the digits with certainty. So on the last example, I think it was like 17, between 17 and 18. So we would definitely say 17. But we also have one additional estimated digit. We call it the doubtful digit. So when I looked at that picture on the last slide, I'd say, well, it's probably about 17.5. But some of you might say, oh no, it's 17.4. And some of you might say 17.6. So the doubtful digit has a little bit of uncertainty in it. And sometimes you'll see them written as plus or minus 1 or plus or minus 0.1, something like that. Don't be too worried about that. But do realize that if all of us made that measurement, we would all come up with numbers that are slightly different. And hopefully they'd be around 17.5, but you never know. People measure things in many different ways. So again, all measurements are going to have some uncertainty in them. We record all the ones with certainty and one more that may be a little uncertain, have a little bit of plus or minus. The total number of digits to express the number is called the number of significant figures. So in that last example, 17.5, I'm going to call it, that would be a 3 sig fig number. And the 1 and the 7 are known. I think everybody would agree with that. But the last one, which in my case was 0.5, there may be some variance. So if you measured it, maybe it's 17.4, and you measured it again later, maybe 17.6, a little bit of uncertainty. So you can see here how scientists are interested in the number of significant figures as well as what exactly is the doubtful digit. And the doubtful digit is always the last number. And again, it may vary a little bit depending on who's looking at it. 65.07 grams is a measurement I made one time. That number has 4 significant figures, the 6, the 5, the 0, and the 7. The last digit, the 7, that's the doubtful digit. And sometimes even the technology, the electronics would say 65.08 or 65.06, something like that. But it's the best guess at that time of what that value is. Here's some more examples. 54.07, that's a 4 sig fig number. And the last number, the 7, that's the doubtful or uncertain digit. And that usually means it's got plus or minus that number. So that would be, in this case, something like 54.06 to 54.08. It's our best guess, literally, as to what that is. The second number has a lot more significant figures. It's got 1, 2, 3, 4, 5, 6, 7 significant figures. A lot more sig figs. The last digit, though, once again, that's the uncertain one. So you can see that there's going to be a variance maybe between 7 and 9 or plus or minus that amount right there. That would be the doubtful digit's uncertainty. Zeros in significant figures are a little weird, and I need to talk here a little bit about what scientists do with them. The non-zero numbers, 1 through 9, are pretty easy, but the zeros are weird. So let's go through these honestly kind of boring things here, but bear with me, okay? If you have a 0 between non-zeros, then that 0 counts. So in 69.08, the 0's in the middle, that's all those numbers are significant. 4 sig figs, and the 8 would be the uncertain digit or doubtful digit. However, when zeros are at the beginning of the number, they're not significant. So here's an example, 0.0089. All those zeros in the beginning there are what I call placeholders. They tell you where the 8 and the 9 start on the number line. Obviously, 89 is different than 0.0089. So in this number, only the 8 and the 9 are significant. They're the only ones that are meaningful. The 9 is is the doubtful digit. Another way to think about this, we could write 0.0089 as 8.9 times 10 to the minus 3. Anything in scientific notation is significant, which is kind of a cool thing. But if you can write it in scientific notation, that's going to be a nice way. And it also happens to show what the significant figures are. Zeros at the end of the number are a whole nother thing. If the zeros are at the end and after the decimal point, they're meaningful. So 2.50 would be 3 sig figs. This 0 is not only after the decimal, but it's also after a non-zero, which is nice. But 25.00, it would also be everything is significant. I like to think of those kind of numbers, or chemists are lazy. We wouldn't write 0.00 unless there was a meaning. That's the meaning. If you have a 0 at the end of a number, but before a decimal point, and the decimal point isn't showing, these are tough. They may or may not be significant. So for example, 1,500 kilograms. By default, I would assume it was a 2 sig fig number, but in reality, it's hard to say. Like maybe the first 0 is significant and the last one isn't. Or maybe they all are significant, who knows? You kind of have to know more about the number to tell if those zeros are meaningful or not. We could write that number as 1.5 times 10 to the third if only the first 2 digits are significant. But if the first 0 is a significant number, you could write 1.50 times 10 to the third. And if both zeros are significant, you could write them as 1.500 times 10 to the third. I love writing these kind of numbers in scientific notation because then there's no question if they're significant or not. But without the dot there, by default, I would assume that they aren't significant and it would be 2 sig figs. But really, you kind of have to know. Ask your instructor if you're uncertain if those kind of things are significant or not. So here's just some examples. Let's go through them and see what's happening here. 94.072, there is a 0, but it's between the decimals. That's going to have all numbers significant, 5 sig figs. 0.0834 has zeros at the beginning. They don't count for significant figures. We could write that 8.34 times 10 to the minus 2. So there's 3 sig figs. Same thing on the next example. This is as the 2907 is preceded by 2 zeros. Neither one of them are significant. We could write that 2.907 times 10 to the minus 2. So there's 4 sig figs. The next one, zeros are after the decimal. And again, this is kind of the chemists are lazy thing. We wouldn't write those zeros unless there was a reason for it. So all numbers there are significant. All 138200, that would be a 6 sig fig number. The next one, 23,000 with no dot showing, is one of these ones where who knows? All right, by default, I would assume it's just 2, but in reality, it could be all 5 of them, or 4, or 3, etc., etc. If you see one of these problems from a chemistry instructor, you should ask them how many sig figs there are. If you do happen to see the dot, like on this last one, then you've got 5 sig figs. The dot tells you that you have significant figures all the way up to the dot. So the 000 there do count. So be on the lookout for that dot. If you see, for example, 10 without a dot, I would assume that was 1 sig fig. But if you saw 10 with a dot, that would be 2 sig figs. The dot just means count the zeros for sig figs. This is an example of a thermometer, all right? And you can see there's 30 at the lower one and 35 here. So it would be 31, 32, 33, 34, etc. And the liquid inside doesn't look like it's mercury because that's kind of a silver liquid. But anyway, the liquid is definitely between 32 and 33. So we would definitely say 32. It's not 33, but it's more than 32. And if you would estimate the middle one, I'd say, yeah, that looks about like a 0.5, like halfway through. But again, you might look at that and think, oh, no way, Russell, it's 32.4. Or you might say, oh, no, it's 32.6. So we have 2 known for sure values and then the doubtful or uncertain digit after that. This is just an example of how this stuff rolls. Significant figures in calculations is another part of this whole ball game we got to talk about, because you could have a really good experimental value and you'd multiply it by something that was done kind of cheesy, and the answer that came from your good measurement and the cheesy measurement is going to be limited by the cheesy measurement. It's going to basically mess up all the work you did. Scientists are really concerned with this because sometimes you'll get really good data, but if you multiply it by something which hasn't been done very well, you won't get a good answer. So we need to record numbers in calculations using only the correct number of significant figures. The calculator is going to give you a gazillion. Sometimes these numbers go on forever and ever, and that's awesome mathematically. But in science, where we're worried about the measurement, we're going to cut them off at the correct number of significant figures. So we'll talk about how to do that with both multiplying, dividing, and addition, subtraction. So those large numbers that are going to pop out of your calculator, we won't usually use all the data. We're going to use just a small subset of them, and we'll round them off to the correct number of significant figures. And remember, if you round something, the first number you drop, if it's between 5 and 9, you add 1, and if it's between 0 and 4, then you just leave it alone. And I'll show you examples of that here coming up. When you multiply and divide, it's a pretty chill process. The answer can't have more sig figs than either of the original numbers. So let's look at an example. Let's say that you looked at your car, and it traveled 278 miles, and it took 11.70 gallons of gas to make it happen. And you're like, well, I wonder how many miles per gallon I got. No problem. Welcome. Oh, science. But anyway, this is a dividing problem, obviously. And what you would do, your answer should be limited to the smaller number of significant figures. So 278, that's 3 sig figs. And 11.70, 0 after the decimal, so the 0 counts, 4 sig figs. So your final answer here should be 3 sig figs, 23.8. That would be the correct way to do these kind of problems, all right? You limit it to the smaller number of sig figs that you put in. So 3 divided by 4 sig figs, you should get out 3 sig figs. This applies to multiplying too. If you took a 3 sig fig number and multiplied it by a 4 sig fig number, you'd only get 3 sig figs out at the end as well. When you add and subtract, it's a little bit different though. You want to use that doubtful digit that we talked about, the last digit of the number. And the final answer can't have more digits after the decimal point than either of the original numbers. Another way that this is sometimes expressed is you want to cut it off at the larger doubtful digit. Here's an example where someone took 3.18 liters and they added in 0.01315 liters. Now, notice that the 3.18, it stops at the second spot to the right of the decimal, or the 8. And the second number there stops 1, 2, 3, 4. It stops at the 5th spot to the right of the decimal. So what the adding and subtracting rule is then, is that we're going to cut it off at the larger doubtful digit. And another way to think about that is we don't know what's to the right of the 8 on 3.18. Like maybe it's 000, but not very likely. It's probably something else. So we don't have any confidence in what these three numbers are right there. So we're going to cut it off where we do feel confident about the numbers. And even though the 8 is the doubtful digit, we feel better about using that than we do some made-up numbers to the right of it. So this number would best be expressed 3.19 liters, or 2 digits after the decimal point. So again, 3.18 was 2 digits to the right of the decimal. The other number was 5 digits to the right of the decimal. We're going to cut it off only 2 digits to the right of the decimal. That's the largest doubtful digit. It's a little weird, but you'll get used to it. We used the multiplying and dividing a lot. We used adding and subtracting though once in a while too. If you need to round your number, remember 5 to 9, make it bigger. 0 to 4, leave it alone. So again, if the first digit you remove upon rounding is between 0 and 4, just drop it and ignore all of them. However, if the number is between 5 and 9, then you want to round it up. So here's some examples. 2.4271, if we're going to raise it up to 2 sig figs, we're going to cut this number off after the 4. And the first digit you drop is 2. And 2 is between 0 and 4. So we're just going to ignore the 271, not do anything. The number is just 2.4. So again, you only look at the number to the right, the first number to the right that you're going to drop. You ignore all the other numbers. They could be 9999999. Who cares? You're only focusing on that number immediately to the right, the first number you drop. 4.5816, if we want to round this up to 2 sig figs, 2 sig figs means we cut it off after the 5. So on this problem, we're going to focus on the 8, the first digit drop. We don't care about any other numbers. That 1 and the 6 are like unknown to us. They can be 99999, whatever. However, in this problem, 8 is between 5 and 9. So we're going to take that 4.5 and round it up by 1 unit. It would be 4.6. If that was 4.55, we'd make it 4.6. If it was 4.59, we would make it 4.6. But if it was 4.54, we would keep it at 4.5. All right, that's the difference between a 5 and 9 that you're dropping and a 0 and 4 that you're dropping. The factor label method of unit conversions is just a way to convert one type of unit into another unit. And again, remember, like we talked about earlier, when you're doing a type of a measurement in science, you have to have a number and you have to have a unit. So 5.2 is the number, centimeter is the unit. Here 16.237 is the number, and grams is the unit. Factor label method is useful when you want to turn one kind of unit into another type of unit. So let's say, oh, Russell, I hate your metric system. I want to turn centimeters into feet. Okay, you could do that. Or you want to turn grams into pounds. That's where this factor label method comes in. And factor label has lots of different names. Dimensional analysis, the same kind of thing. But anyway, all of these things, if you're going to convert one unit to another, you have to have what's called a conversion factor. And you have to make sure you're very aware of your units before you convert things over. So for example, if you have 4 quarters and you want to turn them into dollars, you would say, all right, 4 quarters is $1. That would be your conversion factor in that problem. On the other hand, if you had 3.7 times 10 to the 5th seconds and you wanted to turn it into minutes, you would use the conversion factor of 60 seconds per minute. So again, the labels are really important, but you do need that conversion to go from one type of unit to the other. And these conversion factors, again, big surprise, just are relationships that convert one type of unit into another. And some of them are easy and some of them are a little weird. There's 2 examples here that you're probably familiar with. I already babbled about the second one, the 4 quarters per $1. And another one that if you're in the United States anyway, you probably have used before, 12 inches per 1 foot. Now, conversion factors can be written either way. You can write it 12 inches per 1 foot, which is on the left, or you could write it 1 foot divided by 12 inches. Same thing. Conversion factors can be flipped one side to the other. And here's the other example. 4 quarters per $1 would be the same as $1 per 4 quarters. And depending on what you're converting, you might need one or the other. Here's a more esoteric version, but you may have seen it before. A kilometer is 0.6214 miles. So you could write a kilometer on the top, 0.6214 miles on the bottom. But there's nothing wrong with flipping it. So 0.6214 miles on the top divided by 1 kilometer would be equivalent to the one on the left. You can flip them either way you need to. There's lots of ways to write these again. So you could write it 60 minutes equals 1 hour, and that's fine. However, in the stuff we're going to do, it's more helpful to write them as one of these, where you have a true numerator and denominator, something on the top and something on the bottom. 60 minutes per hour could also be written like this with the annoying per. If you don't want to take the time in Microsoft Word or Google Docs, you could write it with a slash, which is okay. But the very best way to write it is usually like this, all right, or like that one right there, either way, where you have a true numerator and a true denominator. And in chemistry, that's a really cool way to do these. And I'll show you examples of how this works out. There's nothing wrong with using the other methods, like having the per in there or writing it all in one line. But for what we're doing, and especially if you're learning this stuff, I do recommend the numerator-denominator version. Some of these conversions are considered exact. So for example, there's always going to be 4 quarters in $1, and there's always going to be 60 seconds in 1 minute. But we're also going to see a lot of conversions which are not exact, all right? So for example, density of water is about 1 gram per milliliter. That's roughly right, but we're going to see there's actually better ways to do it. And that's where the significant figures come in. If a number is exact, like 4 quarters per dollar, it's considered to have unlimited significant figures. On the other hand, most of our conversion factors will have some kind of significant figure component to it, so we'll have to think about it, and we'll see this here in a little bit too. You've got to have the units cancel when you're doing these problems, all right? So let's, for example, say that we have 26.22 miles. You recorded this on a trip, and then you're feeling guilty, and you're like, oh, Russell said units are so much cooler in metric, so you want to convert miles to kilometers. All right, no problem. It's not that bad. All right. So in this problem, we're starting with miles, and we want our final answer to be kilometers. And when we do this kind of problem, you've got to have the miles cancel. Like, you don't want to have any miles in the final answer, and I'll show you what I mean by that here in a second. Now, earlier we saw how a kilometer was 0.6214 miles. And notice here what I've done on this slide. I started with 26.22 miles, and I used the conversion factor of 1 kilometer, 0.6214 miles. Notice we have miles on the top divided by miles on the bottom. And in math, anytime you have 3 over 3, or x over x, or any number over any number, they always cancel out and go to 1. And that applies to units as well. So in this problem, miles over miles they cancel out. They go down to just 1. And the only unit we have left is kilometers. So in the final answer here, which is 4 sig figs, by the way, because these are all 4 sig fig numbers, the final answer only has kilometers. The miles cancel out. So again, this is important. We're going to see lots of different kinds of conversion factors in chemistry, and some of them may be a little weird to you at first. But the idea of all these problems is you almost always know what you're starting with, like in this case, miles. And you want to make sure you have a miles on the top and a miles on the bottom, so they cancel out. And it might be like moles over moles. Who knows what the units are going to be, but you want to have one on the top and one on the bottom. And then the desired unit, which in this case is kilometers, that's always going to be on the top in this case. So kilometers is sticking around, the miles cancel out, and you're good to go. These are considered exact conversions. Kilometer is 1,000 meters, etc., going on from there and there. All of the metric conversions are considered exact, so that's a kind of a cool thing. So 10 to the 9th nanometers is 1 meter. That would be an exact conversion, all right, etc. Now, here's some other ones. 12 inches is always equal to a foot. 5,280 feet is equal to a mile. An inch is 2.54 centimeters. kilometers. Those are ones we won't use as much, but in the real world of American units, that can come in pretty handy. A centimeter cubed is equal to a milliliter. That's considered exact. Again, under mass, here's some more metric things. So milli to grams is exact, kilo to grams, etc. Pound, 454 grams. This one I would be a little suspicious of. Sometimes you'll see better versions for that. But anyway, you get the idea. These are things that sometimes people will use. So in theory, these conversions all have unlimited significant figures. All right, they're always going to be exact, and but almost all the other types of conversions we're going to see are going to be inexact. They won't have. So we'll have to think about significant figures for those, and I'll show you some examples of that. How many hours are there in 3.5 weeks? Okay, so 3.5 weeks seems like a pretty good amount of time, but it might be nice to know like how many hours there are. So weeks is our starting unit, 3.5 weeks, and we want hours at the very end. That's going to be the only unit left standing at the end of this problem. So we're going to need some way to go from weeks to hours, and maybe you know automatically how many hours are in a week. I don't know how many hours are in a week, but I do know that there are 7 days per week. All right, and there are 24 hours in a day. So I'm going to take two different conversion units and combine them in order to answer this problem. So when I see a problem like this, I want to first of all figure out what the starting quantity is. And 3.5 weeks is the starting unit, all right? Like how many weeks we're starting with. Then I'm going to have to figure out some conversion units, some conversion factors. So like 7 days is 1 week, and that's exact. 24 hours per 1 day, that's considered exact, unless you're an astronomer. There is sometimes deviation in that, but we'll say it's exact for right now. So, in order to solve this problem, start with the 3.5 weeks. Then you want to convert weeks into days. So this first weeks is in the top, and this week or weeks is in the bottom. So if we were to just stop right there, the answer would be so many days. So if you wanted to find how many days are in 3.5 weeks, 3.5 times 7 would give you that answer. But that's not what we're after here. We want to go on to hours. So now that days are left, you want to have some kind of conversion unit where day is in the bottom. So this day in the top in the numerator divided by this number day in the bottom will cancel out, and now you've got just hours. So if you go 3.5 times 7 times 24, and I encourage you to do that in your calculator, you will get to two significant figures, 590 hours. All right, 2 sig figs is what you're looking for in this problem. If you know how to do this process, everything in chemistry will fall for you. I kid you not. We'll have some kind of weird starting unit. You'll have some kind of weird conversion units, and some of them will be exact like these, but more often than not, they'll be sig figs. And you'll plop them together. You want to make sure the initial unit cancels. If there's other units, you make sure that they cancel as well. The only unit left standing should be what you want, which in this case was hours. You're good to go. This process is simple, and yet it is really, really powerful. So if you spend the time like figuring out, you'll be good to go. Here's another problem, all right? We want to figure out how many quarters a tourist is going to need to travel 555 kilometers. Now, this tourist has a car, and the car is getting gas 22 miles per gallon. That's the gas mileage, apparently. And gas at this point is $1.37 a gallon, and that seems a little low, but that's okay for right now's gas prices. Anyway, no problem. And also, because it's in kilometers, and the speed and the miles per gallon is the gas mileage for the car, we're going to need a kilometer to mile conversion. 1.61 kilometers per mile is what we'll use. So there's a lot of weird things here, but it's the same kind of process. Now, 555 kilometers, that's our starting unit, all right? And at the end of the day, all right, we want to know how many quarters there are. So we're going to start with kilometers, and we're going to end with quarters. And along the way, 22 miles per gallon, that's one conversion unit. Gas is $1.37 a gallon. So you can see here how gallon and gallon are connected. So we'll make those cancel out some way. We also have 1.61 kilometers per mile. So you can see that's where this kilometer here will cancel out with the kilometers turning into miles. So hopefully you're starting to see like how this stuff is all coming together. So just like before, start with your starting unit, 555 kilometers. We're going to have lots of conversion factors. 4 quarters per dollar, said that's an exact thing. 22 miles per gallon. Now that's actually a sig fig number because we probably could have gotten better. We probably could have figured out to a tenth of a mile how much it was, stuff like that. That's one I would consider to be an experimental number. All right, we could have done better, we could have done worse, but that's what we've got. So 22 miles per gallon, that's a 2 sig fig number. The price of the gas is also significant figure based. If you look carefully in gas stations in the United States, it usually says like 137 with a little 9 right there. It's like 137 and 9/10. It's the most weird system I've ever heard. But anyway, the 137 is a sig fig number. It was not exactly what's going on. So that's going to be a 3 sig fig number. And 1.61 kilometers per mile is considered an exact conversion. So in this problem, we're starting with 3 sig figs, 555 kilometers. We've got 3 sig figs here, but notice that this number is only 2 sig figs. So when you throw this all together, all right, you want to start with kilometers and you want it to be canceled by this kilometer, and that's going to push us into miles. Then we want this mile to be canceled by another mile unit, and that's that number right there. So we get into gallons, and then gallons will be canceled out and we'll have dollars. Remember, we're after quarters for whatever reason. Okay, $1 is 4 quarters. Now, this arrow system is kind of messy and it doesn't always work real well, but for some people, they dig it. You can make like a path through the woods of these problems, like following the units. So you want kilometers to kilometers and you want to cancel those. So that means 555 kilometers is on top, the other kilometers will be on the bottom, and you just keep going through until this all works out. Try it on your own. If you want to pause the video and try it, and then I'll show you the answer here in just a second, that would be fine. But assuming you're just moving on with it, which is totally fine, I completely understand, that how this works out, again, you start with 555 kilometers. You want to make sure kilometers on the top is canceled by a kilometers on the bottom, and that's what happens right there. So at the end of this first part, you have miles as your new unit. But you want to go on. So then miles to miles, we talked about earlier. Miles on the top has to be canceled by miles on the bottom. So at this point, we've got 1 gallon, all right? Or gallons would be the units we'd have. That would be a better way to say it. But we don't want to stop with gallons either. A gallon of gas is apparently $1.37. So that's one way to cancel out the gallons. They cancel out and you have then dollars that are left standing. And then finally, you want to have quarters as your unit. So $1 on the top is canceled by $1 on the bottom. Quarters finally are left together. So in your calculator, you would go 555 divide 1.61 divide 22 times 1.37 times 4. That should give you to 2 sig figs, 86 quarters. Now, notice there I said divide and multiply. You don't hit enter between them. You literally just go through. And every time I say divide, you literally put divide in your calculator. So again, try it. 555 divide 1.61 divide 22 times 1.37 times 4 equals enter, whatever your calculator says. That should give you the right amount. And that's a really cool thing. Don't hit enter in between each one of those. It'll just waste your time. I'm what they call a lazy chemist. I like to do things the most efficiently. So that's why I'm teaching you all of my secrets. Pretty exciting, huh? Anyway. Now, volumes and stuff can be read through a graduated cylinder, which is what we saw earlier. A beaker will work. In the upper right corner are what they call volumetric flasks. Those are the very most accurate ways usually to do it in the lab. The little line on the glassware shows you some number. So you can look down right there, it says 25. If you'd fill the liquid up to that line right there, that would be 25 milliliters. When people measure liquids, it's from the bottom of the meniscus. The meniscus is like this kind of curve that you see. Most of our liquids we deal with have kind of a downward curve like that. So if you were recording 25 milliliters, you would look, first of all, you'd look straight on. Don't go up or down because it looks funky that way. You'd go straight on, and if the liquid literally touched that thing right there, that would be 25 milliliters. And they have different sizes of these things and stuff like that. Density is a useful conversion factor that goes between the mass of an object and the volume of an object. All right. So density is mass over volume. And there's an old joke about what weighs more, a ton of feathers or a ton of bricks. And the joke is that, well, people think, oh, bricks, are really heavy and stuff like that, and feathers are light. Well, of course, the bricks weigh more. Well, no. If you have a ton, that's the weight or the mass, that would be equal. Now, the volume of a feather is quite a bit different because of the density. Like if you tried to punch a bunch of feathers, your hand would go right through. There's not a lot of mass per unit volume. You try and punch a brick, and I'll tell you that, it hurts pretty bad. You don't want to punch bricks. The density of a brick is quite a bit more than the density of a feather. So you could have a ton of feathers. It would take up a huge volume of space, but it would be a ton. A ton of bricks would not take up too much space. They'd both be a ton. They both have the same weight, but the volume is quite a bit different because of the density. So in chemistry, this density thing can be pretty cool, and all objects have it. Now, usually solids are expressed as grams per centimeter cubed, while liquids in chemistry are usually recorded as grams per milliliter. And if you want to convert one to the other, it's fine. The cool chemists, I guess, use centimeters cubed for solids and milliliters for liquids. It's not a big deal. But all of these things have different kind of densities and stuff you can record. Now, here's another example, which is also factor label as well. Mercury has a density of 13.6 grams per milliliter. That's the density of mercury. How many liters of mercury are there in 42.7 kilograms of mercury? So in this problem, we're going to start with 42.7 kilograms. That's our starting unit. And we need to somehow get it into liters. And right now, we have this thing. Now you can see that kilograms looks kind of like grams and liters looks kind of like milliliters. This is also going to give us some practice with the metric system, how the metric system works. And if you remember from earlier, a kilo is 1,000. So there are 1,000 grams in a kilogram. A milliliter is a very small amount of unit relative to the liter. So if you go back to the notes, it's 0.001 liters in a milliliter, or as most people will say, 1,000 milliliters per liter. So what we're going to do on this question, we're going to take our kilograms and turn them into grams using the metric system. Then we'll go grams to milliliters, and finally milliliters will turn them into liters. So we're starting here with 42.7 kilograms. Sorry, I kind of wrote over that. I guess that was kind of sloppy. Conversion factor 1 is the density, 13.6 grams per milliliter. But we also need liters to milliliters and kilograms to grams. So you can see kilograms and kilograms. This kilogram will be on the bottom to cancel this kilogram, this starting unit. Then we'll go this grams to this grams in density. And finally, milliliters and milliliters will cancel. We'll have nothing but liters. So mathematically, here's our starting unit, 42.7 kilograms. Kilograms on the bottom, so the kilograms cancel. 1,000 grams on the top converts it into grams. This next part is when we're using the density. Here's the grams on the bottom, and that cancels this grams right there, so we have just milliliters. And then because we want the answer in liters, 1,000 milliliters on the bottom cancels those out, and we have liters as the only unit left standing. It's the only unit which hasn't canceled out into 3 sig figs, 3.14 liters of mercury. Cool. Temperature is another one that we'll use a lot. Now, there's 3 scales in science that we use, and by far the most important ones are what they call Celsius and Kelvin. And Celsius is like the standard type of temperature when you're in Canada, England, most of the world, basically. But here in the United States of America, we still use the Fahrenheit system, and that's fine. Fahrenheit is fine. When I listen to local TV and radio, they will record their things in Fahrenheit. However, in the lab, Celsius is so cool because it's more of a metric thing. Now, in calculations in chemistry, excuse me, the Kelvin is really, really handy. And so Celsius and Kelvin are the 2 scales we're going to use a lot. But it's nice to know how to go back and forth between Fahrenheit as well, just because that's what Americans do, for better or worse. So we're going to talk about how to go in between all 3 types. In the ideal chemistry experience, you would record your temperatures in Celsius, and for math calculations, you would convert your Celsius values into Kelvin, or vice versa. However, because the United States uses Fahrenheit, it's nice to go between Fahrenheit and Celsius too if you need to, and from Celsius to Kelvin. Note about Kelvin. Kelvin temperatures for chemistry are always going to be positive numbers. You can't have negative Fahrenheit, you can have negative Celsius, but you will never, in chemistry anyway, have negative Kelvins. Also, technically, Kelvin temperatures should not have that little degree symbol. Notice how there's degrees Fahrenheit and degrees Celsius. Technically, it's not degrees Kelvin. And astronomers and photographers a lot of times will use degrees Kelvin, and it kind of drives me crazy, but that's okay. Just try to not use degrees when it comes to Kelvin. Officially, that's the right thing. And again, ideally, in a regular chemistry world, you'd record everything in Celsius in the lab, and then Kelvin values would be used in calculations, and you can go back and forth, etc. Now, going from Kelvin to Celsius and Celsius to Kelvin is pretty easy. You're going to use this 273.15 number. Now, remember that Kelvin temperatures can never be negative, but Celsius can. So you want to add 273.15 to the Celsius temperature to get Kelvin. On the other hand, because Celsius temperatures can be negative, you want to take the Kelvin temperature and subtract 273.15 to get the Celsius values. So going Celsius to Kelvin, Kelvin to Celsius is pretty easy, not too big of a problem. Fahrenheit is a little bit weird. Notice how the freezing points of water in Fahrenheit 32, in Celsius 0, and the boiling points of water in Fahrenheit 212 and in Celsius 100. And nerdy chemists like me think about things like this. The difference between those two in Fahrenheit is 180, and the difference between those two numbers in Celsius is 100. So what that means is there's this weird conversion of 180 over 100, or if you cancel out some of the zeros, 1.8 times as large as the Fahrenheit degree. And you've got to take into account this 32 degree difference between the freezing points too, so it's not too bad. So again, if you have to go from Fahrenheit to Celsius or Kelvin or the other way, I usually go Celsius to Fahrenheit or Fahrenheit to Celsius, and from Celsius you can go to Kelvin, or if you're starting with Kelvin, Kelvin to Celsius first and then Celsius to Fahrenheit. It's not too bad if you do it that way. Here's a comparison between different values, and again, kind of the important parts here: freezing point of water and boiling point of water, and you can see how they really change. Now, the difference in Celsius between 0 and 100 is 100 degrees. The difference in Kelvin between 273 and 373, which is what you can figure out on your own, is also 100. So the difference between them is the same. That's why you can just add or subtract that 273 chemistry, go Celsius to Kelvin, Kelvin to Celsius, no problem. But freaking Fahrenheit, it's 1.8 times different than the Celsius we saw earlier, and you've got that 32. These formulas can be used for going Fahrenheit to Celsius or Celsius to Fahrenheit. Now, this 9/5, if you put it in your calculator, that's 1.8. So Fahrenheit equals 1.8 times the Celsius temperature plus 32. All right, and that's something we'll do once in a blue moon. If you figure out the Celsius starting with Fahrenheit, this 5/9 is like 1 over 1.8, and you multiply that by the Fahrenheit minus 32. This is a little bit uglier, but that's the same kind of thing and stuff to do. So if you can just cross out the 9/5 and put in 1.8, this 5/9 would be 1 over 1.8, and either way is fine. Pick the one which works best for you. Notice that in starting with Fahrenheit here, you subtract 32 first, and then you basically have times 5/9, or times 1 over 1.8. The other one, it's 1.8 times the Celsius plus 32. That's the only place where it can get a little bit weird. Here's an example. Here's Mars. Temperature that's often on Mars apparently is minus 70 degrees Celsius. Whoa. Let's convert that into Kelvin and into degrees Fahrenheit. So if we were curious. All right, so the things we'll need: starting factor minus 70 Celsius. If you want to turn it into Kelvin, we're going to take that minus 70, the Celsius temperature, and subtract 273.15 to get the Kelvin. On the other hand, Fahrenheit, we're going to take that 9/5 or 1.8 and multiply it by minus 70, then add 32 to get the Fahrenheit. No problem. So anyway, in Kelvin, minus 70 plus 273.15 gets you 203. By the way, notice that minus 70 had a dot. That means that 0 is significant, and we want to stop our answer at the ones spot. So you can see that the 0.15 there was cut off, as we just did it right there. Down here, 9/5 times negative 70 plus 32 is how you find the Fahrenheit. 2 sig figs in this case 2 sig figs out. We're adding though numbers that stop at the first decimal point to the left, so that's where we want to stop at the end. Pretty chill. Online, you can find lots of calculators that will convert these things for you automatically. I recommend you do them just to double check your answers, but it's also nice to be able to do it yourself too. Okay, that's it for chapter 1. Thank you for going through all this with me. Now the next steps will be to focus on problem set number 1. That'll give you experience trying some of these problems. And then of course, quiz number 1 will test your knowledge to see how you're doing, make sure you're good to go. If you have questions on any of this stuff at any time, please reach out to me. I'm more than happy to help. Really glad to have you here. Have a wonderful day.